All right, so the things that are, let's continue with regards to PNjunction. If you recall, in the last lecture, last couple of lectures, we have derived this equation, J equal to Q. How would you write a expression for, how do you remember an expression for current? QV by KT minus 1, of course, for a PNjunction is there. How would you remember, there are two terms. How would you remember the first term? So it's a minority carrier current in P-type and it's diffusive current. So minority current in P-type would be, obviously depends on Ni square over Nd, that's the minority carrier concentration, times this, and diffusion of holes divided by the length, right? And similarly Ni square over Na, and in P-type Dn by Ln, right? So this is the expression for current that we had obtained. And one of the central assumptions in this particular one here, so we look at the depletion region here, Xn and Xp. So one of the, if you recall, this expression is actually based on Jp Xn plus Jn Xp, right? So it's a strange sum of two currents, because normally you're required to sum up at the same place, the two current, but this is at this. And so there's an assumption that Jp Xn equal to Jp minus Xp. Jp Xn is equal to Jp minus Xp. The two currents are continuous. Similarly, Jn at Xn is equal to Jn at minus Xp. That's an assumption assuming no recombination. Or actually one should not use the word assuming negligible recombination. Negligible recombination within depletion region. Now, so all right, so summary of some of the things that we have done in the last lecture was we had derived this particular expression here, which we also call as the ideal diode equation. Ideal diode equation. We had derived this, and there were several assumptions in the derivation. One of the assumption was negligible recombination within the depletion region, because we were assuming this current continuity. Jp at Xn is same as Jn at minus Xp. Jn at Xn is equal to Jn at minus Xp. We are assuming that the current, so we are P and N, so we are assuming that the current here at this point Jp is the same as the current at this point here. That's the first one. Jp Xn is Jp at minus Xp. While we know that Jp at minus Xp should be equal to Jp at Xn plus a recombination current, Jr. Right? The current that enters here at this particular point is not the same that the current that exists at this particular point. There is a recombination. If you want to prove this, just write the whole continuity equation. Del P by del T equal to minus 1 over Q, del Jp by del X. If you're not convinced, recombination is 0, Jp is, G is 0, so this is G minus R, right? And put this to 0, there's no generation, no external generation rate, and use this equation, minus 1 over Q del Jp by del X, and what does it tell you? This tells you that 1 over Q del Jp by del X equal to R. And therefore it tells you del Jp by del x, minus, right? Minus equal to R, or J is equal to minus QR, right? Recombination rate. Del Jp by del x is minus QR. So it tells us that if you integrate this, then it tells you that Jp at minus xp is Jp at xn plus the integral of q. What is this Jr? Jr is nothing but integral of qr dx minus xp to xn. So the PN junction current has, if we take that into account, has an additional current Gr, recombination current. So if I were to do things accurately, I should have added here, along with this, A plus a recombination current. So the whole issue then becomes is, what is this recombination current? How do we calculate it? So we have to look at recombination rate. And we said recombination rate, we have this big expression. We have this expression, so let me take this expression from here, copy it. Here, this expression here. This is the expression that we have here, which tells us the net recombination rate. So it's a long expression. It depends on where the defects are and all that. And we said for simplicity, we will take the defect level at middle, ET at middle. And so this equation then R turns out to be NP minus Ni square. And we'll also take the following, tau N equal to tau P, all this simplicity. Tau N equal to tau P equal to tau, some recombination lifetime, tau, and this is 0. So this equation then becomes N plus P plus 2Ni. It simplifies our analysis, 1 over tau. Okay? Now, if R is positive, it gives us the recombination, which means if NP is larger than Ni square, if NP is larger than Ni square, we have recombination, according to this expression. If NP is less than Ni square, we have generation. Right? So we have a general expression for how recombination and generation occurs. Now, we have to take this R, and note that we have to take this R and we have to evaluate it minus xp and xn. We have to evaluate it within this depletion region. We have to evaluate this within this depletion region. We have to do this R times dx. Right? We have to do this R times dx, and we have to evaluate it within the depletion region. And we note that within the depletion region, last lecture we had proved that NP is equal to Ni square e to the power qv over kt. Product NP is Ni square e to the power qv over kt, whatever voltage we have applied. So if we are looking at forward bias, then R for us becomes equal to NP, because Ni square we can neglect, NP, N plus P plus 2Ni. R becomes this within the depletion region. Because Ni square, if you want, okay, we can write this as R, we can write it as, let's be a little bit more accurate, Ni square e to the power qv over kt minus 1. Fine, we can write it like this. So if we look at R, and we see, well, R, because N and P are varying within the depletion region. And, if I look at this is P and this is N, so P is starting from here and then sharply reducing here, N is also going like this. And this graph actually doesn't illustrate very well, because it's starting from a very high value. Let's say P is, 10 to the power 16, and maybe falling to, let's say, 10 to the power 12 or 10 to the power 11, right? So it's falling to a fairly, this thing here. Fairly small value, 10 power 16 to 10 power 11. So there's a rapid variation within the depletion region of hole density and electron density. And obviously, if we look at this R, we will find that R would be sizable where N and P are minimum. If N is very large or P is very large, you can easily, show that the maximum value of R will occur where N and P are actually equal. If n is very large, then you have a problem. If p is very large, you have a problem. So the maximum value of R max will occur where n and p are, basically R max occurs where n equal to p. And if n equal to p and we have n equal to p, so it becomes ni e to the power qv over 2 kt. We get this here. So the maximum value of R max that turns out to be ni square e to the power qv over kt minus 1. And now note that n and p are much larger than this, so you put 2 equal to ni e to the power qv over 2 kt. So the maximum recombination rate, according to this, then maximum recombination rate R max is equal to ni by 2 tau e to the power qv over 2 kt. That's the maximum recombination rate. Ni over 2 tau e to the power qv by 2 kt. That's the maximum recombination rate. And in a symmetrical junction, it will occur in the middle. But we have to compute this, R dx. So what we are saying is this R dx, when you integrate, it will come from a region very close to the maximum. So if we were to plot within this depletion region, this is minus xp and xn, your R will look almost like this. Very sharply varying function with this is R max. So what we are saying is this integral R dx is equal to some R max times some effective width. There's some effective width of recombination, some R max into W effective. So we are sort of simplifying it and saying it's W effective, and then the problem becomes what is W effective, and we are not going into that. So the point is, after doing all this, we are realizing that the recombination current, JR, then if we look at this, is equal to Q Ni over 2 tau e to the power qv over 2 kt, this R max, multiplied by some W effective. So the recombination current is a 2 kt current, qv over 2 kt, while the other current was, the other current that we just wrote, if you go back, is e to the power qv bar kt. So we get two components of current. The JR then we can write as some prefactor e to the power qv over 2 kt here. So we have some of these two currents, and this is where we were in the last lecture. We were looking at also this thing here, the reverse bias current here. So that's the forward bias current, right? Forward bias current has 1 kt current here. You should realize where the first component comes from. It comes from injection here and recombination in these regions here. And where the second component comes from, recombination in this particular region, right? These are the two components of current. And so if somebody were asking you, when does the first term dominate? Well, the first term dominates at medium sort of voltages, medium or high voltages, while at lower voltages, this particular term will dominate here. And we've given you full expressions, and you can calculate the two components of current at different biases. Right? Now, the other complication in a PN junction is, before we come to this, so if I were to plot on L and J versus V, so note that this is there. The other complication is, at higher biases, the current also deviates from exponential behavior. So at higher biases, the current again, doesn't follow the exponential behavior. L and J versus L and V doesn't follow exponential behavior. And the reason why it doesn't happen is we have a number of assumptions which break down. For example, low-level injection, which are all related together. Low-level injection assumption. And we have, the other one was voltage applied drops across the junction. So we had this, all of these tend to break down in this particular region as you go to higher one. So the issue is, how do we calculate this? Note that once the diode is no longer exponential, the characteristics is no longer exponential, is actually going towards linear. It's tending towards, this behavior is tending towards ohmic behavior, tending to a linearity. Okay. Now that's not very good. Because remember, you're using diodes in various applications and you want the diode drop to be very small. You don't want diodes, significant drop across the diode here. Now in this region here, if you go in this region, the voltage drop across the diode increases rapidly with current. Because note that in the exponential region, the voltage drop is kT by Q, ln 1 plus I by Is. It increases as log in this region here. But in the linear region, the voltage drop will be some constant plus I times R. It starts increasing linearly with current. So you don't go into that particular region. You avoid this particular region here, ohmic region here. Most applications will not go into that. Okay? So there is a sort of maximum current that I can use. So if somebody were to ask you, up to what current can I operate my PN junction diode, such that it's still exponential, it's not gone into the ohmic region, up to what current can I calculate? Okay? So the idea is, well, the question then we can ask is, a simple way of doing it is, just look at this low-level injection. When does low-level injection approximation fail? Because the moment the low-level injection approximation fails, all these problems, they all start. It starts deviating from exponential behavior. And low-level injection approximation is very easy, right? The low-level injection approximation, if you recall, was that the injected carriers, if I look at del P in X, in N-type region, so let's look at del P Xn, should be much, much less than the doping. If you are looking at PN junction here, so we are saying low-level injection means carriers injected into this N region should be much, much smaller than the doping. Or the other way is del N minus XP should be much, much less than Na. So now you look at which side is lightly doped. When will this condition get violated? This condition will get violated. So let's look at the first one. Del P Xn is much, much less than Nd. So del P Xn is what? Ni square over Nd e to the power. Let's neglect the one part there, e to the power qv over kt. Right? We are saying when this is much, much less than Nd. So effectively you are saying much, much less than Nd. So, and the other one is telling you Ni square over Na much, much less, Ni square over Na e to the power qv over kt is much, much less than Na. So on which side is this condition likely to get violated first? The lower doped region. So you look at both the regions of the diode and you look at which one is the lower doped region, N-type or P-type. So let's say the lower doped region is Nd. So now you have to look at when does this condition get violated. So you have to put some number on what is much, much less than. Okay, so typically we put it 1/10. So so much, much less than, so we'll say Ni square over Nd e to the power qv over kt when it becomes Nd by 10, let's say. Right, then you will start getting violation of that particular condition. So you have Ni square over Nd e to the power qv over kt less than or equal to Nd by 10. So from this equation you will get e to the power qv by kt. At what voltage does this happen? So how do you calculate the maximum current? The maximum current would be I max will be equal to area, whatever is the area of the junction, multiplied by your expression for current. Okay, so let's see where I can find space. So so maximum current would be I into area into our usual expression Qni square dP by Lp Ni square over Nd plus Nd plus Q Ni square over Na dN over Ln, right? Now here is where we had e to the power qv over kt minus 1, e to the power qv over kt. Now this is what we determine from this one here, e to the power qv kt by here, from here. So what you do is e to the power qv over kt and you go ahead and substitute this value and you will get an expression for what is the maximum current up to which you can operate your PN junction. If you try to operate it beyond that, well, it will start entering into ohmic region. is entering into ohmic region, and that's not good for you. The voltage drop across the PN junction becomes this thing here. So that's how you, what is the upper limit of operation? Well, you will say, well, operate it till this particular point here. Well, now this ND by 10 is debatable. You can take ND by 5. Some people may take even equal to ND. That kind of a thing is, the boundary is fuzzy. You could take it here and there, okay? All right, so that determines the upper limit of operation of this thing here. Lower limit, well, at what point does your diode fail to obey ideal diode equation QV by KT? Well, you will look at the recombination current and find when the first term, the normal current, starts becoming equal to the recombination current. And so that will decide, it starts to deviate here also. So that would decide what is the range within which your ideal current equation is valid here. Now, if you're wondering, isn't it very easy to increase Imax? Simply. So when people design PN junctions, those who design PN junctions, depending on the application, say you are using a PN junction in motor control, right? And it's operating at 1 ampere. It's operating at, those things are operating 1 ampere. Obviously, you'll choose Imax to be larger than 1 ampere so that your diodes that are used there they can handle that much current properly here. Suppose there's another application which uses 10 amperes. Well, for that diode, you will design Imax greater than 10 amperes. So if you're wondering, why don't I design a diode whose Imax is greater than or equal to, say, 1000 amperes? Why don't I do that? Then it will be valid for all the diodes, all applications. Just design one diode for 1000 amperes. So no matter which application you take, 1000, 100, 50, 1, it's going to be useful for all of them. What is the problem? No, so look at, if you will see, if you go back and see what is e to the power QV over KT, what is it equal to? What is this term equal to e to the power QV over KT here? Is equal to ND square by 10 by NI square, right? Correct? ND square by 10 NI square. So if you were to use, and so this is equal to ND square by NI square times 10. So if you were to increase the value of Imax, how would you do that? How would NI is fixed, DP is fixed, DN is fixed, LN is fixed. How would you do that? You would try to increase ND. You would try to make the junction higher and higher doping. So you would try to increase ND, and this is another thing, if time permits, we'll see that. As you increase ND, right? As you increase ND, what happens is the another parameter called breakdown voltage, it starts going down. Right? So as you try to make Imax higher, by increasing ND, well, your breakdown voltage starts to go down. Now you may say, well, I will not touch ND. Why don't I increase the area? I can increase the Imax by increasing the area, right? Make the area larger. What happens then? Larger area means occupies more of the silicon. So the cost goes up. The cost starts going up. So are you seeing, let me put a very simple trade-off. Are you seeing that there is a trade-off? I'm not exactly putting Imax times breakdown voltage by cost is like a constant. Something, I can put here some M, some N, and some zeta or something. There's a trade-off there in a PN junction. If you try to increase Imax and you don't touch the cost, well, your breakdown voltage will go down. Why? Because how will you increase the Imax? You will touch ND and the breakdown voltage will go up. If you don't touch breakdown voltage and you try to increase Imax, well, then the area has to increase and the price that you have to pay is cost. So you're seeing in the design of the PN junction, there is this fundamental trade-off, Imax breakdown by cost. And that's the reason why you find I don't have one unique diode. Why are there hundreds of diodes in the market? Why are there hundreds of diodes in the market? Not just one diode catering to all the application. It's because of this trade-off here. Some application require a certain breakdown voltage, a certain kind of maximum current handling capability. So you design a diode for that. If you're thinking I'll design a general purpose diode applicable for all of them, so you will have to make Imax very high, a general purpose diode. You'll have to make this very high, and then you'll make also then this very high, right? You'll make the cost also very high. So you can design a very high current carrying capability diode, a very high breakdown voltage, but then a very high cost, and nobody will buy it. Right? You may design, but nobody will buy it. So this is the reason why you find, in short, why you don't find one single transistor, one single diode, one single BJT, one single MOSFET which caters to all the applications. Why? Because of the trade-offs. The trade-offs are there. You have to, and you're seeing one trade-off here. Imax, breakdown voltage, and the cost. And there are like this, there are many trade-offs. There's a trade-off between, we don't have time, there's a trade-off between speed and breakdown, speed and other things. How fast a diode switches also is related to other things. Okay? All right, so with this, I want to end the forward bias. So I hope you understand what is happening in the forward bias. Okay, the reverse bias part here. Okay, so let's look at the reverse bias part here. All right, the reverse bias part. So we have. Let me draw the diode here. So we have to keep drawing this here. So let me write down again the ideal equation, Q Ni square over Nd dP over Lp plus Ni square over Na dN over Ln e to the power QV over KT minus 1. So in reverse leakage, although we have derived this equation by looking at only with the forward bias in mind, right? We were talking about injection, diffusion, recombination, and all of that. We can, if you take voltage as negative. So what this equation is implying, that for reverse bias, this equation is implying J equal to minus, if you apply a significant reverse bias, it's implying Q and these two terms here. Right? It's implying that. And just as we did the forward bias equation, if you don't want to use this equation, you can go back to first principle and derive this exactly by saying J equal to Jp xn plus Jn xp, then making the argument Jp xn is diffusive, and all those similar kinds of things, and you will end up getting this same equation that you will get here. Okay, but remember, one major assumption in this is that it's neglecting generation recombination in the depletion region. It's only considering things happening outside the depletion region. What I was showing you in the last lecture is this. If you look at this first term, the first term, if you look at J equal to Q Ni square over Nd dP by Lp, right? This is one term of the reverse leakage current. Reverse leakage current minus this thing that's one term, and the second term is obviously similar. If you look at this particular term can be written as Q generation rate times Lp. This is what I was trying to tell you, that this equation is looks like this, and we were looking at what was happening here. If we look at, so we were saying, well, if I were to plot then the hole density here is almost negligible, and then excess hole density goes like this here. Excess hole density, if we plot delta P at x, excess hole density here is minus Ni square over Nd, and excess hole density here goes to 0 here. Far away, excess hole density is anyway 0 here. So this term, which looks like a diffusion term here, Qni square over Nd dPLP, is actually equal to Qg times Lp. What is happening is there's a region here, and generation is taking place in this particular region. Electrons and holes are getting generated, and the holes are diffusing. The holes are diffusing, and then they are collected here. Now, how did I show this generation rate? Well, I said go back to this equation, this big expression here, and you write down what is the generation rate in the N-type region, outside the depletion region. What is the generation rate? Okay, so now note that Np is much less than Ni square, because Np is always equal to Ni square e to the power Qv over Kt, and V is negative. So Np is much less than Ni square. So if you start looking at what is the generation rate, I don't want to go into that again, because we had seen that you can write that this first term is the generation rate due to generation of carriers in the N region. Similarly, the second term, if I were to write, is generation here, in all this region here. Generation on the P side. So carriers are getting generated on the P side, and electrons and holes, in this case, the electrons move in this direction. What is missing is that there is a generation inside the depletion region also. If you want the story to be complete, you have to take into account generation within the depletion region. And now what happens is, if I look at generation inside the depletion region, so if you recall, R equal to Pn, simplified expression was Pn n minus n square into 1 over tau, P plus n plus 2Ni, right? This is our simplified expression. And we are talking about reverse bias. Okay, so tell me what will happen here. So this is Xn, this is Pnn, Xn, and this is minus Xp. Okay, so if I start looking at this region here, what is Pnn equal to? The product of Pnn equal to Ni square e to the power Qe over Kt, right? V is negative. So what can we say? V is, let's say you apply minus 1 volt. What can we say? Pn equal to approximately 0. Right? P into n is Ni square e to the power Qv over Kt, and V is minus 1. So what can you say? P and N are sort of negligible, very small. So the product of P and N is very small. Okay? So why is the product of P and N very small at this point? At this point, at the edge of the depletion region, N is not small. But what happens is, P is negligible. P is negligible. Why is it the product so small here? Well, P is not negligible. P is equal to Na, but N is negligible. Right? So as you go inside the depletion region, what you find is both P and N are negligible. Both P and N are negligible. Okay? If you were to draw, so look, so first thing I can do is R, then R becomes equal to, basically equal to minus G, generation rate, equal to Ni square over P plus N plus 2Ni over 1 over tau. Now you start plotting P and N inside the depletion. We are talking about inside the depletion region. You start plotting P and N inside the depletion region. What do you think is happening? And you will see just by here. Plot P. P is, what is the value of P here? Everybody agrees? Na? Na. And then as you go inside, what will happen to P? What is the value of P here? 0. Almost 0. So what happens to P? How fast does it? Note that this is equal to 10 to the power 16. So what you find is On a linear plot, it will look like this. Because where does it have to go? From 10 to the power 16 to 10 power 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, it's just negligible here. So if you, on a linear plot, if you could measure hole density and on a linear plot you plot, it will look like this. So P and N, you will find is almost very small inside the depletion region. Very quickly it becomes very, very small. Similarly, if I were to plot N also becomes very, very small. So the idea is over most of the depletion region, or the generation rate, note that this is also equal to minus. So generation rate could be written as Ni square. You can neglect both P and N and equal to 2Ni over 1 over tau. Over almost the entire depletion width, or equal to minus Ni by 2 tau. This is the generation rate. P and N are negligible inside. The moment you go inside the depletion region, both P and N become very, very small. So what is the total generation current? Generation current is, remember, Q times G integrated from minus xp to xn dx. So this turns out to be Q Ni over 2 tau. Sorry, Ni is not Ni, Q Ni by 2 tau into effectively the depletion width. That becomes my total generation current. Q Ni by 2 tau into W. This is the generation rate. From here, this is what is happening here. So in reverse bias current, then what we can write is the total current I can write J equal to J, assuming is minus, so you can write this as Q Ni square over Nd dP by Lp plus Ni square over Na dN over Ln. That's the first term. Plus Q Ni over 2 tau into W, depletion width. That's the total current. And if you plug in typical numbers, you find this term is larger. The second term is greater than the first term for silicon. If I take silicon PN junction, I'll find that the second term typically is larger than the first term. So many times this, and if it's significantly larger, then J as an approximation becomes equal to Qni over 2 tau into W. Most of the reverse bias current in a PN junction, silicon PN junction, where is it coming from? Generation within the depletion region. The outside regions, they don't contribute. They contribute, but not that significantly. Okay, I would suggest all of you to, we have given examples to compute both of these quantities here. Go ahead, put some numbers, dP, Lp, dN, Ln, calculate both these numbers and see. So this becomes the significant number. And this is what we were discussing, brings us to the notion of, if I look at forward bias current, the forward bias current we were writing as, again, the forward bias current we were writing as Q Ni square over Nd, dP over Lp, plus Ni square over Na, dN over Ln, e to the power qV over kT, minus 1, plus there's a recombination current. But if you are at a higher bias like 0.6, this doesn't matter. Only the first term matters here. And so you write this as J equal to Js, e to the power qV over kT, minus 1. And you call this as the reverse saturation current. You call this the reverse saturation current. Okay, is reverse saturation current? There is a component like that, but then there is another component, which turns out to be much larger. So that's why this GS that you measure from forward bias is not the reverse saturation current. If you actually measure reverse saturation current, you will measure this quantity here. While if you look at the forward bias current, you will measure this quantity GS here. You will calculate this JC. So that's the distinction between the two here. Okay. Now, we have limited time, and in limited time, there are two other things that I want to do. So this is the, so all reverse bias current is coming from generation. Generation outside the depletion region, generation inside the depletion region. Okay. That is the source of carriers. Okay. The one other thing about reverse bias is, note that when we draw this junction here, so you're noting that most of the, this is P and N, this is your Xn, and this is Xp. So what you're noticing is that there is a, if I focus on, let's say there's an electron hole pair generated, the hole, because of the field, the hole is going to go like this, the field is in this direction, and the electron is going to go in this direction, right? That's the basic, and like that, the carriers are being generated all over the depletion region, they're going like this here. Now, if you keep on increasing the field, we have said that a phenomena called impact ionization comes into picture. Impact ionization comes into picture. So now what happens is, this electron, note that this electron which starts from here, and as it moves, it causes impact ionization. So what you end up with is one electron and one hole. Now this electron also moves, both of them move, and maybe they also cause impact ionization. So what you find is, as a process, what the result is, you're getting avalanche multiplication. You're getting a multiplication. You may generate one electron pair only in the depletion region. That electron moves, causes impact ionization. So you get two electrons. Those two electrons move, they also cause impact ionization. You get four, and then there is a multiplication process that is occurring. If you apply a sufficient field, if you reach a critical field, EC, this avalanche multiplication process becomes very, very high. This process becomes very high, you get breakdown. Now, why is the breakdown so sharp? You know, we normally call, if you recall, if I were to plot J versus V, well, forward bias is okay, fine, and then current looks here, and then boom, sudden increase. Why does it happen like this? Because the impact ionization is a very strong function of electric field. If you recall, we have given you expression of alpha n, impact ionization coefficient. They were exponential functions of electric field. So what happens is, as you change the electric field, impact ionization coefficient is small. But then, you know, you keep on increasing the electric field, and then suddenly the impact ionization coefficient takes off, because it's an exponential function of field. So because of that, the breakdown occurs at a very sharp point because of that particular case. And typically, breakdown in PN junctions, we model it by saying, once the field, because impact ionization is related to field, once the field reaches a certain critical value, the impact ionization coefficients become large and the breakdown occurs. So for every semiconductor, what we do is, we tend to specify what is that critical field at which the impact ionization becomes very significant. For silicon, we use a field like approximately somewhere between 3 to 4 times 10 to the power 5 volt per centimeter. So if you have to calculate at what voltage will my PN junction break down, how would you do that? All you need to do is, for a PN junction, you need to calculate, in a PN junction, there would be a maximum electric field. Where is that maximum electric field? At the junction. If the maximum electric field crosses EC, breakdown will occur. So the calculation of breakdown voltage is actually very easy. All you need to do is find out at what voltage the field reaches a value of 3 to 4 times 10 to the power 5. That's all. And you know a fairly good value of breakdown voltage. And we already know how to calculate field. Given any PN junction, we saw how to sketch the electric field, voltages and all of that, how to do that, how to calculate field, we already know. So essence of breakdown is this. In almost all PN junctions, breakdown will occur by an avalanche multiplication process. Only if you go to a very specific junction which is P plus, if you go to a junction which is P plus and N plus. Know that if the junction is P plus and N plus. Now the moment you say P plus and N plus, what should come into your mind? Very, very narrow depletion width. So you have a, see, if you ask yourself, like I have an electron here, right? Why is this electron not able to go here into this? We say there's a barrier, right? There is a barrier which is preventing. Now you take a P plus N junction. What happens to the barrier? Very, very thin. And once it becomes very, very thin, what happens? Tunneling occurs. So once you go into a very, very heavily doped junction, well, the barrier tends to become transparent. The electrons are able to tunnel through the barrier. And so you get a new mechanism of breakdown which is called the Zener mechanism. The Zener breakdown mechanism that is there, that's because of the tunneling phenomena. But in most of the diodes, we don't encounter it because most of the diodes are not P plus N plus. We never make such diodes. P plus N plus. We don't make them. They're usually P plus N. Right? So, and one of the reasons why we don't make it is because of this. If you make P plus N plus junction, the barrier becomes very thin, tunneling starts to occur, you get large reverse bias current. Even if breakdown doesn't occur, you get large reverse bias current. So the diode is not very useful for you. Okay? Doesn't become useful for you, and so one side you can keep heavily doped, the other side you have to keep lightly doped. Both sides heavily doped is not possible. And it's for that reason what you find is okay, so it's for that reason that you find your okay, let me keep it at that level. One last thing about a PN junction is capacitance. Capacitance and switching. Capacitance and switching. So the first aspect of capacitance is actually very simple. I have a depletion region. I have a PN junction. I have a charge. I have a depletion region here. I have Xn, I have minus Xp, and I know that voltage is whatever voltage I apply. I know that there is a depletion charge Qj. Depletion charge Qj is equal to Qnd into Xn, same as Qna into minus Xp. So we know we can calculate these, right? And anytime you change the voltage, the junction charge changes. So del Qj by del V gives you the depletion capacitance. Anytime you have a charge which changes with voltage, so you get a depletion capacitance. And I'm not deriving it, we have expressions, it's easy to show that dip is equal to epsilon by depletion width. And if you want to be total, it will be equal to the area. So that's the junction capacitance, epsilon by W into area. Okay. Depletion capacitance is present in this. It's just simply change in charge with change in the applied voltage gives you a junction capacitance here. So it's there in both forward bias, there in reverse bias, so that is not an issue. And we can derive, we know expression for W equal to whatever square root and all that, you can calculate the expression. The issue is one of what you've all heard of is a diffusion capacitance. Okay, diffusion capacitance. What is this capacitance? That is the source of a lot of difficulty or misunderstanding that is there here. Now, for the sake of simplicity, let's take a junction which is, to simplify, let's take P plus N junction. Now in a P plus N junction, what is the source of the current? If it's P plus N, the current is predominantly, is it due to holes or is it due to electrons? The holes will get injected and there would be hardly any electron injection, because injection depends on the doping, inversely with doping. Okay? So it's primarily a hole injection device here. All right? So where is this? So and diffusion capacitance, you've also heard that is only in forward bias. Not in reverse bias. So when you apply forward bias here, so what is the source of this diffusion capacitance? What do we mean by diffusion capacitance here? So remember, at one point, you need to look at that any time I have charge inside my device, and the charge changes with voltage. I have capacitance, right? That's the definition of capacitance. Now you look at P plus N junction. You look at this device here, and you see what is really happening. When you apply a forward bias, what happens? You inject holes into this region here, right? Let's say there's a depletion region here. You inject holes in this region here, correct? Now, if you look at this region here, fine. Look at this region here, this part. So I have holes. How do the holes go? Exponentially, right? They're going like this, and if it's a long diode, it goes here, right? This is P. Let's write it delta P, excess holes. But this region is neutral, correct? This region is neutral. So how do you have excess electrons? Excess electrons also go like this. Delta N also goes like this, right? Electrons also, because it's neutral. Amount of excess holes is equal to amount of excess electrons. So now, where did these holes come from? These holes, where did they come from? They came from? Note that the holes came from, the holes went like this, right? If I look at this particular point A, where did the hole come from? From left. From which terminal? From here, right? Eventually from here, right? Positive charge came in from there. Where did the electron come from? There's an electron also there. Where did the electron come from? The electron came from here. So there is a region in space where you have excess holes and excess electrons, right? The holes came from one terminal. The electrons came from the other terminal. And you have charge. And now if you increase the voltage, what will happen? More holes will come in from there. Electrons will come in from the right side. And the charge will increase. So it's an interesting case because you're saying the region is neutral. The region is neutral, so it doesn't have overall charge. So some people get into this confusion. Sir, the region is neutral, there is no charge. How come I have a capacitance? So for them, the answer is this. If I take a parallel plate and if you connect it to a positive voltage here, right? You get a positive charge here. You get a negative charge here. Overall, it's neutral, right? Anyway, it's neutral. I mean, the two plates, if you consider them together, overall is neutral. Here also, this region is neutral. Is there a separation between charge? Yes. You don't require a physical separation as such. I mean, there is a separation. The electrons are in the conduction band, the holes are in the valence band. So there is charge. And they've come in from two different terminals. One has come in from, just like in a parallel plate, one has come in from here, the other has come in from here. Similarly, one charge has come in from here, the other charge has come in from here. Yes?
So will that be instantaneous capacitance but for a short moment?
No, it takes time for the charge to come in.
I mean, as they increase the voltage, then extra charge.
It will respond after a certain time, but after a while, it will acquire that charge. So there is a charge. So what we are saying is, in this region, if I look at, in this region, there is a charge QP which has come in from the P side. And that charge QP del Q by del V is nothing but diffusion capacitance. Why are we calling it diffusion capacitance? Because that charge came in through a diffusion process. Who supplied that particular charge? The whole current. The whole current is what? Diffusive current. It's a diffusion process which supplied that particular charge. So there is a charge in N region. Holes and electrons. And they came in from two different terminals. As you increase the voltage, more charge has to come. As you decrease the voltage, the charge has to go away. And that's the source of your capacitance here. So there's one more capacitance which is sitting in your PN junction is C diffusion equal to del Q by del V. What is this QP? QP will be equal to Q delta Px dx from integrated from xn to basically infinity, if it's a very thick diode, or xn to the device length.
Can we also call it as differential capacitance?
No, these are all, we are talking about differential capacitance, change in charge with voltage. We're all, how much charge increases or decreases. So we're talking in that sense only. So QP is Q del P dx xn to L. You have expression for del Px, you can actually calculate QP. And for a P plus N junction, you will find it very interesting that QP is equal to J times tau. If you just do the integral, you can show that J times recombination lifetime. Charge equal to the total current flowing through the device multiplied by tau. We have taken a P plus N junction for simplicity. So QP equal to J times tau. And therefore, this capacitance that you see here is nothing but del J by del V times the recombination lifetime tau. Capacitance. Now, just think for a moment. You are in a forward bias condition, right? You've applied 0.6 volt or 0.65 volt, you are in a forward bias condition. You have a lot of charge here, right, in this region, diffusion charge. Suddenly you apply a reverse bias condition. What will happen? Now you don't want any charge to be there in that place. Reverse bias means no such charge. What happens to that charge? This charge which was there here, right? All this charge which was there here in forward bias, now you've suddenly applied reverse bias. What will happen to that charge? Two things happen. It tries to go back. It came from, see the holes came from P side, it tries to go back to the P side, right? And the other thing is recombination, right? So how fast, suppose we forget for a moment that is going back to the P side. How fast will the charge disappear? How fast will the charge disappear will depend on recombination lifetime. Because yes, there are two sources. One is going back to the P region, the other one is recombination. Okay, so both are there and both are, depending on the situation, both are significant. But for a moment, if I just look at recombination process, then the charge will disappear because of recombination. That depends on the recombination lifetime. Now, you want recombination lifetime to be fast or slow? Because what does it mean to go from forward bias to reverse bias? Forward bias means lot of charge. Reverse bias means no charge. So to make a transition from forward bias to reverse bias, I have to remove all this charge here. And to remove all this charge, I need to have tau, which is very low. A diode which has a recombination lifetime of 1 microsecond versus a diode which has a recombination lifetime of 1 millisecond. The 1 microsecond diode will switch off very fast compared to 1 millisecond. So what it tells us is we want tau to be small. We want tau to be low for a diode to switch quickly. But are you seeing a price that you have to pay? If you keep tau low? Yes, first of all, the issue is how do I make tau low? Right? How do I make recombination faster? But suppose there's a way of making recombination faster. What do you lose? Just go back and see this thing here. What did we say about reverse leakage current? Qni by 2 tau. So if you try to make your diode fast by making tau low, what do you end up getting? Large reverse leakage current. So you start getting into a problem with that. So you are seeing another trade-off. Trade-off between reverse leakage current and the switching speed of the diode. You get into that issue. All right. So these are, so if I were to summarize in a diode, what are the important things in a diode? The important things in a diode is how much current can it conduct? What is the highest current that my diode will be able to conduct? I max. What is the breakdown voltage of the diode? How much is the reverse leakage current? Reverse leakage current. What is the switching speed, F? And say, what is the cost? Right? Maximum current, breakdown voltage, leakage current, frequency, cost. Cost is always, even if it's not said, cost is always there in your mind. So these are the things that are there in your mind here. And now you can see so our goal was, we didn't get time, our goal was to give some value here, let's say 1 ampere, to give something here, say 500 volts, leakage current 1 nanoampere, frequency 1 megahertz, cost, well, we'll leave it open, minimum, right? So give a set of specs, and now your goal is to, from here, design a PN junction. Design a PN junction, which means what are my doping levels? So design means what? ND, NA, what value of ND, NA will you choose? What value of recombination lifetime will you choose? What is the area you will choose? You have to figure this out. ND, NA, tau, and area to satisfy these specs.